Hello, students. Today we want to talk about some additional theorems for computing derivatives. The first result will be called the product rule. That is, we need to know how to compute the derivative of a product of differentiable functions. The second rule will be the quotient rule. And so when we think of having to differentiate a quotient of functions that are differentiable, a rule would be very useful. We are aware of how we can use the definition of derivative to compute derivatives, but we're already starting to see by the abstraction that we can grow the envelope, so to speak, and create theorems that are more efficient and get us to the finish line much more quickly. We need that, and as future STEM professionals, you need to have that efficiency when you work with the calculus. And the last thing we want to talk about are the fact that we can actually differentiate derivatives. That is, we can now look at the derivative as a function and apply the derivative again. And we call taking a derivative of a derivative a second derivative. And then, of course, we can continue the process. So that's what we call higher order derivatives. And so we want to say something about that too, because as you get to curve sketching, we're going to think about a shape operator, which is actually the second derivative. And then, of course, in calculus 2, we will use theorems that require many orders of derivatives of functions in order to write power series. So the derivative can be iterated, and that's a useful mechanism to create mathematics that can be very useful to us. So let's get started with the product rule. What I'd like to do is state these theorems and then go over maybe one of the proofs so you can see how the definition and the theory work together. So first, let's go ahead and state these two very important rules, the first one being the product rule. So we'll just call these theorems. And we'll start with the product rule. So the idea is that we suppose, just like we do in all these, suppose f and g as functions are differentiable on an interval I. So we want to assume that they have differentiability on a common set of content. And now what we want to do is take C in the interior. So I'm going to say element of int for interior of I. So basically, we don't want to start with an endpoint. We know what a left and right derivative is, but we want to take a point that we find in the interior away from the endpoint. So that's why we say int of I. So C is not an endpoint. Then the product, so these are all twofers, as we say, we get two for the price of one. Then the product FG is differentiable So the product FG is differentiable at C. And, well, I mean, it's good to know that the product of two differentiable functions is differentiable, but the second idea that we get from this is an actual formula. So when we say F times G derivative at C, we get a rule that's usually named after Leibniz. Sometimes this is called Leibniz rule. So we have the derivative of F at C times G of C plus F of C times G prime of C. So this theorem is not simple like the derivative of a sum or difference, where you just have the sum of the derivatives or difference of the derivatives. This is a little more complicated. So we don't get the luxury of saying that the derivative of a product is the product of derivatives. That is not correct. So it's actually more complicated. And later on, this will give rise to a very useful antiderivative formula called integration by parts. So this formula does us lots of good. But again, note, and an easy way to remember it is just think, pairing these functions, just think first function, second function. So the first function is differentiated, multiplied by the second. Then add to that the first function multiplied by the derivative of the second. And of course, this gives you the evaluation or the derivative of the product at C. And then, of course, if you want to write this as a function, then you can just switch everything, all the C's to X's, or just start with X's to begin with. So this again, very, very important. And as a computational tool, it is quite necessary. So as you do your mathematics, you do your science, your engineering, this is indispensable. Now, the next theorem that we need, and of course, there's going to be a major result after these two that we'll get in the next lecture. This is called the quotient rule. Now, in this case, we basically do the same thing. We have the same hypothesis. So we suppose F and G are differentiable on an interval I. I'm writing these out again. These are really important, and it's sometimes good just to think about these things. I could just show you the results, but I really do want you to think about these as we go over them. Suppose F and G are differentiable on an interval I. So again, we will take C in the interior of I. And of course, what we're tacitly assuming here is that the quotient is well defined. That is, we have differentiability for both functions at C, and the derivative as we speak, F of C, F prime of C, G prime of C clearly exists. And when I say well-defined, we don't have division by C. That's a tacit assumption, and sometimes we just overlook it, but we are tacitly assuming that the function is well-defined. We have no division by zero. Then, of course, the quotient F over G is differentiable at C. And this has a very, very interesting formula. That is, the derivative of the quotient at C is F prime of C times G of C. So it starts to look like the product rule, but now we have a subtraction sign, F of C, G prime of C, divided by the square of G of C. Now you could put a 2 here like we do in trigonometry, or you can just put the square here, your choice. When we do squares in trigonometric functions and all, we put the superscripts by the notation of the function, just for convenience. So if you wanted to put the G superscript 2 of C, that would certainly be okay. but I want to make it clear that we were dividing by the square of g of c. So again, if you like a function in terms of x, then just replace all the c's with x, and then you've got your function that again, we can treat the derivative as a function if we just basically think of all of the points for which the function has differentiability as its domain. Now, let's look at some examples here, or look at one of the proofs here. We'll go ahead and look at the quotient rule, and then you can actually check the notes to look at the proof of the product rule. They're very similar in how they're executed, but I want you to see how they work. So again, if you remember the statement of the product rule, as we have here, it helps you to remember the statement of the quotient rule, but then of course you have the additional factor in the denominator of g squared. So that's a very interesting result, but both highly useful and necessary. So what we can do, again, is just, I think it's important, like we did with some of the previous results, to show how the definition of derivative gives us this result. And of course, the level of abstraction that we have will apply to any function that has derivatives. And as we combine them into quotients, it will cut down on the tedium that the definition will require us to do each time. So this is really a big time saver. So what we'll say is that g, in this case, we're going to look at the function f over g. So let me start with f. So by definition, f over g prime of c. Again, we're gonna use the fact that differentiability at c implies continuity. That will be an important result here. Will now be the limit as x approaches c of f over g of x minus f over g of c divided by x minus c. So this is just the limit of the difference quotient, where we evaluate the function at x and we evaluate the function at c and divide by x minus c. This is indeterminate. So what we want to do is show that through the process of algebra, we can create an identity that will absorb the troubling x minus c in the denominator. That is, remember, when we write the difference quotient, we are searching for a formula. We're searching for the slope of the tangent line to the function where it is defined. And therefore, we have removed ourselves from the actual function into describing the slope of the secant line, and then allowing x to approach c and deriving a formula that will provide the actual slope of the tangent line where it exists. And so then we can investigate the actual formula and see, will it make sense here, so we can expect to have tangent lines for these points. And then, like I said before, we can certainly treat the derivative process as providing us with a new function and then differentiate again. So what we want to do first is apply a little college algebra. So we'll just write the definition of these items here. That is, we have f of x divided by g of x minus f of c divided by g of c, all divided by x minus c. So what we would like to do is do common denominators here and then move some of the algebra into the denominator, and then add and subtract a term that will allow us to use the hypothesis of differentiability. Unfortunately, as we work through a problem, there's got to be an instance where we use the differentiability hypotheses. That has to, those basically are sufficient to get this result, at least the way we have written this problem. So we've got to set up for that. So let's get common denominators. So we'll have G times G of X times G of C. So we're going to need an F of X times G of C. And then I'll just move over here. We're going to need a G of X times F of C. And now we can just collapse the common denominator, G of X, G of C. Now you're seeing where that G squared is going to come from, and then place it by the X minus C for now. So just a few steps of algebra shows you that our formula is already starting to take some shape. So now what we want to do is what I've suggested. We've got these terms here that hint at the definition of derivative. So what we could do is add and subtract F of C times G of C. Remember, when you add the the version of 0, add and subtract the version of 0, or you multiply by a convenient 1, this is simply a way to elucidate certain properties that are available to us, but we have to make them evident. So now we have F of X, G of C, minus F of C, G of C, plus F of C, G of C, and then of course minus F of C, G of X there. And then of course downstairs, the same thing. And then the nice part about this is that we can now, as we look at what we have, we can move the X minus C into the numerator and have fractional equivalence that will give us the difference quotients that we need. So note here, we have the add and subtract. So these two terms here, we just say add / subtract. Of course, I subtracted first, but the add subtract is the mechanism we're using. And now what you can see is common to the first two terms is the G of C. And then what's common to the other two terms is the F of C. So we'll just factor so that we have the order of the function and the evaluated function for the definition of derivative. So we have the limit now as X approaches C of, if you will, we'll factor the G of C, I'll put a little dot here, F of X minus F of C, and then we'll move up the X minus C for both of these terms. Now next, we're going to factor the negative from these two terms, and we have the common factor of F of C times G of X minus G of C. So again, we're factoring the negative, so we have the order in the difference quotient correct. So that tells us why we have the negative sign. And then of course, downstairs, we just have the G of X times the G of C. So by adding and subtracting convenient terms here, we can now utilize the differentiability hypotheses. And then of course, the quotient rule, which allows us to take the limit of the numerator divided by the limit of the denominator. And then, of course, we can apply the constant rule for limits, extracting constants, and we can apply the sum rule too. So we can decompose the numerator using the limit theorems and then further the ability to see the actual formula. So now we have g of c times the limit as x approaches c of the difference quotient. It's amazing how the analysis works. And then we have minus f of c times the limit as x approaches c of g of x minus g of c divided by x minus c. And then, of course, in the denominator, we can apply the same using the limit theorems, factoring the g of c with the limit process. And then we have the limit as x approaches c of g of x. And of course, this limit we know because of continuity. If g is differentiable at c, then it is continuous there. So this is a continuity result, which we certainly need. And then, of course, now when we look in the numerator, we have g of c, and then, of course, we have, by definition, the derivative of f at c, and by definition, the derivative of g at c. So we're seeing that the hypothesis of differentiability of f and g is sufficient to get this particular result. And so now we can fill it in. So by the hypothesis, we have g of c times f prime of c minus f of c times g prime of c. Of course, I'm not writing these necessarily in the same order. I think I did the f prime first, and maybe then this order was the same. And then, of course, excuse me, the limit here is just g of c. We can just run the limiting process inside by continuity and replace the x with c. So now we just have two copies of c. And now I'll just write things in the right order, or the order that I had before. F prime of c times g of c minus f of c times g prime of c divided by the square of g of c. And that's exactly what we wanted to show. So now, of course, the idea of using the definition of derivative, the alternate definition, gives us a very nice formula. And then, of course, if you want to just apply the formula to the derivative calculation as functions, that's fine too. So what students will often do, again, is replace the c's with x's and write a formula in terms of x. But the main thing here is, like we've been doing, we want to know where it makes sense to define the actual slope of the tangent line. And once we have that, then we can move to the derivative calculation that we have and simply treat it as a function. So the utility that we're going to find between the product rule and quotient rule will only open the door to the fact that we really will need to know how to differentiate a composition, because most functions that we come in contact with fall into those categories. You know, when we have algebraic functions, we have compositions, we clearly have products and quotients, but the composition, it occurs with frequency. And so we would need to know how we could apply the definition of derivative to actually get a formula. Would we know that if we compose differentiable functions that the result would be a differentiable function? We will find that it is, and we'll need to use some results about the actual definition of derivative that will maybe be a little bit surprising, but not too much. So let's look at how we can apply some of the results that we've just talked about. So one thing that we at least want to state are the derivatives of the remaining trig functions. That is, if we have the derivative of sine and cosine, how can we use the new theorems to get the derivative of the remaining four? And since they're basically quotients and we don't have a composition theorem yet, we can use the quotient rule. So for instance, we want to recall, in this case, that the derivative of the cosine at C is just the additive inverse of the sine at C. And the derivative of sine at C is just cosine at C. We did a derivation of this one, and then of course, if you've gone ahead and looked at this, we have the additive inverse here. So we just have to remember the derivative of the cosine gives the additive inverse of sine, or the negative of sine, if that's easier to say. And of course, the derivative of the sine gives us the cosine. So that's really not very surprising when we think they're just, the sine and cosine are just horizontal shifts of each other. So maybe that's not too terribly surprising. And the geometry that you remember from the calculus is already starting to be apparent with us, because now we remember that we had the formula or theorem that if you have an even function, its derivative must be odd. And if you start with an odd function, its derivative must be even. And so we're seeing that play out in these formulas. So that is indeed a good result. So now let's just go ahead and look at the other derivatives. So we'll call this 1, and we'll call this 2. And then 3, we'll write down the tangent. I'll write down the 4 others, and then we'll show how we can actually get some of these derived with the quotient rule. And the ones we don't do, please look through those and verify to yourself that they are indeed correct. So we'll have the derivative of the tangent at C, kind of like we're doing continuity, we just use the basics, right? So we'll have, in this case, let's just treat this as a quotient. So this will be sine over cosine derivative evaluated at C. So now we've got a quotient, so now we can actually apply the quotient rule as we did that we just proved. So this will be, and I'll write this out, we'll have sine prime at C times cosine at C minus sine of C times the derivative of the cosine. So we have cosine prime at C divided by the square, cosine. And now if you want, you can just do squared of C. Like I said before, since we don't seem to have a problem doing it with the trig functions. I don't know why F and G were, or G was any different. But there we have it. And so now what we can do is just go ahead and fill in what that we know here. The derivative of the sine is the cosine. So we have cosine of C times cosine of C minus sine of C. And then, of course, we have the derivative of cosine is the additive inverse of sine. So we've got I'll put in a -1 sine of C. And then, of course, downstairs, we have cosine squared of C. Now, notice here with the minus minus, we get the plus. So this gives us cosine squared of C plus sine squared of C divided by cosine squared of C. So we're like, well, this is nice. And so, of course, the fundamental identity is 1. So we have 1 over cosine squared. And if you like, you can write this as 1 over cosine. And just square the whole thing. So this gives us secant squared at C. Now, I said I was going to list them all, but of course I started deriving it. And so now you can see that when you have a function that is defined in terms of the product, the quotient of differentiable functions, you can use the quotient rule. So now, just as a summary, and this is not something you always expect. As a summary, I'll just write it in one line. The tangent derivative at C is just secant squared. So again, we think of the derivative of secant and where it exists, okay? And that's back to your trigonometry exercises. So again, we know that the secant is 1 over cosine, so it's going to have asymptotes, vertical asymptotes. For instance, when we think of it, we have negative pi over 2, and then we move negative pi over 2, 3 pi over 2. So these odd multiples of pi over 2, just like we learned in pre-calculus. So the interesting part of what you did earlier now helps you to understand where you actually have derivatives for the tangent function, which again is not surprising at all, because the tangent function lives between the primary branch between negative pi over 2 and pi over 2. I've got to wave the hands to get the light to come back on. So here's a nice result. So we'll just box that. So now you're thinking, wow, this calculus is getting kind of interesting. The derivative of tangent is secant squared. Interesting. Now let's go ahead and write down the companion formula, and you can prove this if you want. Similar exercise. The cotangent at C derivative will now be the negative of the cosecant squared, with a similar exercise. So these at least seem to be connected, in the sense the derivative of cosine is the negative sine, the derivative of sine is the cosine, the derivative of tangent is the secant squared, the derivative of cotangent is the negative cosecant squared. So at least you've got the sine and cosine, and then you've got the secant squared, cosecant squared, but again, the additive inverse as you have here. So we're getting this plus minus bit with the derivatives. Now let's go ahead and look at the derivative of secant. Again, when we write this, we are tacitly assuming that the function has definition at C. Okay, we don't start the process by throwing that to the wind. The definition of derivative requires that the function be defined at C. So anytime you're talking about, and this is very important, anytime you're talking about derivatives, you really do need to put forth what's the derivative of, what's the domain of the function, because a tangent line will only exist for a point that has definition for the function. And then of course you have to have the limit of the difference quotient existing. So it's not a simple process, but we want to make sure that when we write something like this, that the tacit assumption is that C is in the domain of the function, or C is in the domain of secant. So sometimes you don't get any surprises. For instance, when we look at tangent, we know that this is not defined at pi over 2. And then of course, as we look to the derivative, well, we didn't really lose anything, did we? I mean, we didn't have the pi over 2 to begin with. but it still makes us wonder that like the cases where we have like the absolute value or the square root function, we do have elements in the domain for which the derivative does not exist. And so that's when we need to be careful about stating the domain of the function. So for secant, let's just go ahead and work this out, and I'll give you the result for the cosecant. But this is likewise very straightforward. So we'll just do 1 over the cosine prime evaluated at C. The prime notation is very useful, and this derivative definition is easy to use. So now you're thinking, well, this is not very difficult. So now we just got the derivative of 1 evaluated at C times cosine evaluated at C minus 1, I just put a little dot, times cosine derivative at C divided by the square of the denominator. Again, looks familiar, cosine squared at C. So of course, the first, we know the derivative of the constant is 0. So this zeroes out. So we have 0 minus, and now of course the derivative of the cosine is the negative sign. I've covered that up, the negative sign. So we have minus, and then we have the negative of sine at C. And then of course division by cosine squared. Now you're thinking when it comes to writing derivatives, of course we could write the derivative like this, but it's standard to write it this way. It doesn't mean that how you express something can't be individual to yourself, but when we look in formulas and calculus books, there's usually a standard form using particular trig identities to write the derivative. So what normally happens here is we do an equal opportunity. We actually leave 1 copy downstairs written this way. Of course, the negatives absorb, and then times, then we do the sine of C divided by the cosine of C. So when we look at this, we're thinking, well, do we stop here? No, now we want to use just basic identities. Of course, 1 over cosine is secant. And then, of course, sine over cosine is the tangent. So we could just write this as the function secant tangent evaluated at C. So the key here is that this is the primary way you see the derivative of secant. It's written as secant tangent. So we'll just write that down. So the derivative of the secant function at C is just the function secant times tangent evaluated at C. Or if you like to write it as the separate factors, that's fine too. Again, we think of secant tangent as a product, and then that's like an F times a G at C. And so you evaluate secant at C and tangent at C. And so that's more in line with how we write a product of functions. And then this, of course, is just the definition. So that should be something that, again, we've used many times. So how you want to phrase these is really up to you. When you look in a lot of calculus books, many times the derivatives are written using a variable x, or they're written using a variable u if they're in an integral table, but very straightforward. Now, just to finish off the list, the derivative of the cosecant looks like this, but it has, of course, the additive inverse, which is not a surprise. This turns out to be the negative of cosecant cotangent evaluated at C, or written in terms of definition, the negative cosecant at C times cotangent at C. So interestingly enough, none of these are completely difficult, but you do need to think about why they are true, and then practice writing them down, and then make an effort to commit most of them to memory, so you have them available. You can always have these on a formula sheet or whatever. There's really good formula sheets on Blackboard. The idea is that we want to use these enough so we're familiar with them. And if you go back through it where we started with the sine and the cosine derivatives, derivative of cosine, the additive inverse of sine, the derivative of sine is cosine, and then we get this plus minus deal with the remaining 4, okay? So the product rule was indispensable for this. So I keep saying the product rule, the quotient rule. The product rule was the first theorem we stated, but notice we are simply using our definition of the other 4 trig terms, and they are all defined as quotients, okay? They're all defined as quotients. And so the quotient rule makes good use of working with these types of functions. And again, you don't think about this when you're doing your basic geometry with the unit circle, but now we find that actually has been a good thing, that we not only got the beautiful geometry of the unit circle, but we also got the symmetry and the arithmetic of the unit circle, which we will definitely continue to use, okay? So what I want to do now is just look at some examples. The nice thing about the quotient rule and the product rule is that they're not overly tedious. You just follow the rule each time you do a derivative, and you can think of these, for instance, in terms of any variable you like. When you look at your homework, most of the functions are written in terms of x, so you can replace the c's with x's and just think of differentiating with an x variable as opposed to evaluation with c. So I have some simple examples here. So let's look at a few. The first one, we're just going to write a function, f of x will be, in this case, let's see what I want to do. Oh yeah, 16x, we've been using the quotient rule, so might as well go ahead and use it again. X squared plus 16. Now in this particular example, we want a tangent line to the curve at -2, -8 So again, when you look at this and you substitute the -2 and the arithmetic here, you get the -8. So this is actually a point on the curve, and obviously we need that. And there are other, if you look in the lecture notes, there are other ways to deal with points that aren't on curves that just use very simple geometry. But when we say a tangent lines are not unique, but we certainly know that the slope of the tangent line at a particular point is unique to that point where the derivative actually exists. So in order to get the tangent line, we need a slope. So that will be the derivative, and then we'll evaluate it and then just use point slope. So first we want to use the quotient rule. So we'll say the derivative of f evaluated at x. Again, this is the same thing as evaluating the function at c. But now what we want to do is just get a formula. All right, so you can write these in terms of c if you want, or you can just stick with the variable. The notation is exactly the same. I just like writing the derivative formula with the c because that's a standard notation, and it's a very convenient one and very nice in terms of notation. So it kind of gives us the realm of looking for all the values of C for which the slope of the tangent line exists. And then we just move to the derivative as a function and thinking of it in terms of an independent variable x because we like x for that. So now we have, again, you can use brackets or parentheses. We have 16x divided by x squared plus 16 prime. Okay, so now this is the numerator function and the denominator function. Of course, we're using f here, so you could think of that as a g and an h if you want. Now, the first thing we can do, I always think it's best to remove as many items of clutter that we have. And of course, the 16 is just a constant, so we can factor that. There's no need to carry that through the calculation. That would be a waste of time. So we have x, and we have x squared plus 16 prime. So now these are just easy polynomials where we can use the power rule, so we don't have to be as pedantic as we were when we were doing the proofs. So now we have 16 here. And now we take the derivative of x, which is just 1. We proved that, remember, so we have 1 times x squared plus 16 with a minus sign. Now, of course, the x is no more, we just have the x, no derivative. And then we take the derivative of the denominator. Of course, we can use the sum rule. The derivative of the constant is 0. And of course, the derivative of x squared is 2x. So we just say times 2x. And of course, we square the denominator, x squared plus 16 squared. So again, what we see, what we remind ourselves of, we can do a little calculation up here. X prime is just 1, and x squared plus 16 prime is just 2x. So these are real simple. So we're using our building blocks to take derivatives. We do derivatives within derivatives. So it's an interesting process by which we come up with these formulas, and they are interesting and very different compared to what we've been doing in our mathematics, or that you have been doing on your road to calculus. So we have 16, and we just want to combine things. So we have x squared plus 16, and here we have minus a 2x squared divided by x squared plus 16 quantity squared. Now, what we want to do is just simply make this a little bit simpler if we can. So notice we can combine. So we have a negative x squared. Don't forget the 16. You know, it's hanging out. We don't want to drag it into the calculation. We just leave it where it is. So we have negative x squared plus a 16, okay, divided by x squared plus 16 quantity squared. So of course the denominator is irreducible. We can't really do much with that, but we can clean this up a little bit just for good practice. So let's factor a negative and then factor the difference of two squares just for practice. So we have negative 16. And then of course, this, if you like, I'll go ahead and write it out. This is x squared minus 16 divided by x squared plus 16 quantity squared. So now this gives us a negative 16. And if you like, you can just type this in as x minus 4 times x plus 4, if it makes it a little bit easier to evaluate. Always your choice. And then of course downstairs we just have x squared plus 16 times x squared plus 16. So I just say x squared plus 16, x squared plus 16. So here's a formula for the derivative that might be a little bit easier for evaluation. And then of course if we were looking for zeros of the derivative or horizontal tangents, we could easily find them, and I'll say something about that. So now here's our derivative. This is our f prime. So now, of course, we want the derivative. So this implies the slope we usually think of as m when we are working in algebra. And this will be f prime evaluated at -2, as we have here. So we just fill it in. So we have -16. So we have a -2. So this gives us a -6. And then a -2 here will give us a 2. And then here we've got -2. So that's a 4 plus a 16. So that's a 20. And same here, a 4 plus a 16, which is a 20. So now we just want to absorb common terms. Notice here, the 16, the negative here, we've got the negative, so they absorb. So we've got what, 4 times 4. And then we have times 6 times 2. And then, of course, downstairs, we got 4 times 5 times 4 times 5. So again, the negatives absorb, which is good. We have to pay attention to signs, you know, just like you've always done. Nothing new there. So the 4s here absorb. And so now what we're left with, we have a 25 here and a 12. So 12 over 25. So that's the slope of the tangent line at -2. So again, the process uses the blocks that we have created before, ladies and gentlemen. That is, we do the simple derivatives, and then we move to the product rule and the quotient rule, especially the quotient rule we see to be very, very useful here. And we just apply the building blocks as we apply the quotient rule. Very simple building blocks, and then it basically just reduces to simple algebra and arithmetic. Really, that's all we do with calculus, just a more tedious arithmetic. And so now we've got the slope and we've got the point. So let's just write this. Here's our point, -2, -8 over 5. So this implies we can say y minus the negative, so that's plus 8 over 5 equals 12 over 25 times x minus the -2. So that's plus a 2. Now, of course, this is fine. This is a line, but usually your homework will ask for an mx plus b form. So just take everything to one side, if you will. This is certainly a form, but we want to work with a form that has been requested of us. So we have 12 over 25x. And then, of course, here, multiply by 2. This gives us what? 24 over 25. We keep things factored when we want to make things as easy as possible. And then we have minus an 8/5. So the 12 over 25, and I guess if you like, you can just put the x right there. Sometimes we put it to the side, but maybe it's better just to stick it right in the numerator where it lives. And then we can get a common denominator of 25. So we have 24, and of course, 5 times the 8 is the 40, so minus 40. So now, of course, the difference here will be a -16. So this gives us 12x over 25 minus a 16 over 25. And so if you will, just go ahead and put the y here and put a box around it so that you don't have to necessarily write it again. So that would be an equation of the tangent line to the function f of x at the point -2, -8/5. Again, this is commonplace in calculus. It's not overly taxing, but these calculations just give you practice using the basic constructions. And so as you practice using these rules, you definitely get better. As you practice the quotient rule, you get better. Okay, your algebra is going to improve. And let me just make a few comments here. Notice if we're looking for horizontal tangents, they would exist at 4 and -4 because the derivative there is 0. So when you factor things, not only do you make it easier to analyze the derivative, but you also make it, in many cases, easier to evaluate. So just as an extra here, so we'll say f prime of x. This is like doing like an f prime of c. We see this is 0 if and only if we've got what, x equal 4. These will turn out to be critical numbers later, x equal -4, okay? So this would be points where we have a horizontal tangent. We've already talked about that, and I know I'll probably end up sounding like a broken record before it's all over, but yeah, this is the case. And then of course the derivative, we don't, we're good to go here. We don't have any infinite tangents. Clearly the denominator is never 0. So let's look at an example where we use some trig functions. Now, I will say something about the product rule, but the quotient rule is the most difficult. And so if you can do the quotient rule, you're in good shape. But I think I'll save the product rule for maybe I think I've got a question here. Just a basic calculation, then for a second order derivative to give you practice with that. So let's look at this. So we have now what we can do just to get some practice, we're going to say y is the function. We'll just say y of x is 7 plus cosecant x. And then we can be more relaxed without all the parentheses. Not because we're being slack, but we're okay. So 5 minus cosecant x. Oh, get the other copy of C here. And what we're asked to do is compute y prime. So this is our standard notation at pi over 6. Now, remember, when we apply the definition, that means x approaches pi over 6, and then we do f of x minus f of pi over 6 divided by x minus pi over 6. Now, of course, we could do that, but boy, that again is a lot of work. We see how much work it is just to work in the abstract, and then as we do individual functions, there's a lot of algebraic maneuvering that has to be done. And so the abstraction of these formulas, that is, we prove them in the abstract, and then we bring it back down to the problems we're working, and we see that we have an easier time of it. And we're grateful for the theorems, because even though sometimes there might be a lot of work to do, it would be simpler than applying the definition directly. So now what we want to do is compute y prime evaluated at x. Again, instead of using the c, we'll just go ahead and use the x from the problem. And again, if you want to continue using the c's, that's fine. No problem there. Just write it that way. Doesn't make any difference. So now we'll have 7 plus cosecant of x divided by 5 minus cosecant of x prime. Now, of course, we don't have any nice numbers to factor here. I mean, we're okay with the way it is, and it's not overly complicated. So we'll just go ahead and apply the quotient rule to this, the numerator function, the denominator function. Now, of course, in the numerator, the derivative of 7 is a 0, but we know the derivative of cosecant is negative cosecant cotangent. So we have negative cosecant cotangent, and we'll do this with the definition of the product by putting both of the x's in. That's usually the nature of doing this when you're less formal. And this would be times the denominator, which is 5 minus cosecant x minus, now we have the numerator, 7 plus cosecant x. So this is really what we call court reporting. We're just typing everything and we're doing a lot of repetitious writing, but it's okay. The derivative of the denominator now, of course, the derivative of 5 is 0, but the derivative of the cosecant is the negative cosecant cotangent, but we have the additional negative here, which absorbs that. So that's just going to give us cosecant x cotangent x. So again, we're using the derivative formula for cosecant, which is the negative cosecant cotangent. So the negatives here absorb. And now downstairs, this very straightforward, 5 minus cosecant x quantity squared. So there's the derivative there. Now, what we usually like to do is try to simplify this so maybe we have an easier time of evaluating. That way we don't have to work as hard. So now let's go ahead and multiply this and see what we have. So we've got 5, a negative 5, cosecant x cotangent x. I mean, you could just say, well, I'll just go ahead and, evaluate it and not worry about it. That's certainly a possibility. And then here we've got the negative negative. So we have plus cosecant squared x cotangent. You're thinking, it's factored, so that's probably not very difficult. I don't think we're gonna, let's see if we're gonna have anything absorbed. So now we've got the minus 7 cosecant cotangent. And then, of course, here we have the, again, we've got the minus, so we have the cosecant squared cotangent. So again, how you decide to evaluate is completely up to you. If we're trying to uncover some properties when we differentiate, we usually have to be a little bit more fastidious because we're trying to look for zeros and things like the last problem. But we also have to remember what the goal is of the problem. So when you decide to evaluate, that's up to you. But we can at least see here that these two terms absorb. So it pays to try to make some effort to simplify, even though we are certainly big fans of factoring, because that usually makes the process simple. So now, if you look here, we've got the cosecant cotangent, but we have a negative 12 copy of that. So negative 12 cosecant cotangent. And then downstairs, we have 5 minus cosecant x quantity squared. So what you can do at this point, you're thinking, well, this is fairly simple. There's no need to try to simplify it anymore. And then you could think, well, we can now do the substitution. So this is the y prime. I'll just go ahead and rewrite that. We see this is the same. So this is what we've done. So now we need to make the evaluation. Now, usually it's simpler if you just break this up into pieces. So we can look at the numerator and then the denominator and then put them together. So here we have numerator. Lots of times it's better if you don't try to look at everything like when I teach integration, break the problem down into pieces so that you have better organization. So we'll have negative 12 cosecant at pi over 6, cotangent at pi over 6. And you don't have to remember, you don't have to memorize anything because we know what these are in terms of sine and cosine. So this is negative 12, and this will just be 1 over sine of pi over 6. And then cotangent is just what? Cosine over sine. So we have cosine pi over 6, sine pi over 6. just keeping it simple. Don't forget the negative there. So we have -12. And then, of course, the sine of pi over 6 is 1/2. The cosine of pi over 6 is square root 3 over 2. And then, of course, the sine of pi over 6 is 1/2. So now at least writing here, the 1/2's absorbed here. So that's simple. And now we can flip up the 1/2. So that's a -12 times the 2 times the square root of 3. So if you will, that gives us a -24 root 3 in the numerator. So we'll just put a box around that for now. Now in the denominator, just breaking it up into pieces, it's probably easier to think about it this way. So now we have 5 minus cosecant of pi over 6 quantity squared. And so now this gives us 5 minus 1 over sine of pi over 6. And we want to square that. So of course, sine of pi over 6 is 1/2. So we get 5 minus 1 over 1/2. Well, that's nice. So that's just 5 minus 2 if you reciprocate it. 5 minus 2. Well, now I'm thinking of that result. I would better keep my power to be 2. So this is 3 squared, or 9. So now this implies, so we've got our denominator. You can do everything in one piece, but since they're kind of busy, if you break it up, it's not bad. When you first start, break things up into pieces. So now we have y prime of pi over 6 will now be the numerator. And of course, we can factor that. We have a -8 times the 3 root 3 divided by 3 times 3. But of course, everything's going to absorb, very simple. The 3's absorb. And then, of course, the root 3 absorbs into the 3's. That gives us a -8 over root 3. So, I mean, nothing wrong with radicals in the denominator. But I'll say this, if you break down the process, for instance, if we have this as reduced as it can be, at least algebraically, we're good. Then you can look at the separate pieces instead of having to try to do, a big fraction and then reduce and copy. So just look at the pieces of it and then put them together, and you have a very simple calculation. So now what we see is that this problem has basically just been reduced to a derivative theorem, algebra, building block derivatives, and then trig exercise evaluation at pi over 6 or unit circle. Okay, so that's why we learn what we learn to study calculus, just so we can do things like this. And now you see, this will be fun to practice, not as tedious as some of the work we've done so far. Just fun practice using algebra and trig that you know pretty well. Now, what I want to do is say something about, let's see, maybe a higher order derivative would be good. This will be using the product rule. Again, now the quotient rule, the product rule is going to seem kind of simple, but that's good. We're all about that. We want ease, and we can find that since the quotient rule is basically the product rule in the numerator, we've already been practicing it. So here we're going to have a very simple function. You won't find this to be difficult. I just want to show you how to take a second derivative. So say we have secant x. Okay, we're not as formal now with the parentheses, but of course, when you do your homework, everything has parentheses. And what we're asked to do is compute. Now I'm going to talk about higher order derivatives. F double prime. You're thinking, well, what does that mean? Okay, so the two tick marks means take a second derivative. So for instance, let's just note, let's observe what we're doing. When we think of the derivative of f at c, we just apply it again. So if we say f double prime at c, what we need is take the derivative of f prime. So we have f prime differentiated at c. So I guess what we do, we're tacitly assuming that c is in the domain of f and that f prime of c does exist. And then we're going to think or see if f double prime of c exists, or find c for which it does exist. So again, this is kind of a cascading thing, and you might can imagine derivatives that have all orders of differentiation, or excuse me, functions that have all orders of derivatives. And we already know some, the sine and cosine, no problem. They just toggle back and forth, right? You take the derivative of sine, you get cosine. You take the derivative of cosine, you get negative sine. So they toggle back and forth. That repetition makes the trig functions very useful functions for solutions to differential equations. I mean, it just, we can't do without the trig functions. So again, think of the second derivative as just being a derivative of the first derivative. So if we formally wrote the definition, this would be the limit as x approaches c of f prime of x minus f prime of c divided by x minus c. So the utility of this definition is clear. You just simply replace f with f prime, and then you're good to go. So once we know how to differentiate, we don't have to keep applying the definition like this, even though we could, we don't choose to. So now we're thinking, okay, is the second order derivative going to give us some additional information like the first derivative? We don't even know what it can do, really. They both will be very useful as we move through the course, and we'll find those out shortly. So again, this just means, like I've written here, if we do the first derivative, then we take the derivative of the first derivative to get the second derivative. So you just do two derivatives, f to f prime to f double prime. So f prime, well, this is easy. So f prime of x is just secant. Now we can write this in terms of a more standard definition. So this is just the derivative of secant evaluated at x. And we know the derivative of secant is secant tangent. And now we'll just write it in the definition form. Secant x, and I'll put a little dot there, tangent x, so you can see that it's a product. Normally we just juxtapose, but the first time we go through, it's nice to put the dots there so you see it is indeed a product. So now this is a product. So in order to get the second derivative, we take the derivative of the first derivative, which is a product. So now we have f double prime of x is equal to f prime of x. So that means take the derivative of this. So now we can just write this as secant tangent prime evaluated at x. So now we'll do the product rule. So of course, if you like, let's go ahead and write this out formally to give you some practice. So this will be the derivative of secant evaluated at x times tangent x. So I'll put in the parentheses here, do it formally, and then plus secant x. Oh, because I don't need my outer parentheses there because I'm not taking a derivative. I mean, that's kind of overkill. So we have secant x, and now we have the derivative of tangent evaluated at x. Again, we just using x's instead of c's now. So now the derivative of secant is secant tangent. So we have secant tangent evaluated at x, of course, writing that formally, times tangent x plus secant x, and the derivative of tangent x we just showed is secant squared. And we'll use the cheap subscript, superscript notation. So now we can now take the definition of the product. So we get 2 copies of tangent and 1 copy of secant and write it in the lazy way. Like that. And then plus secant cubed. Now, when you think about this particular exercise here, and what's important is that all we have to do is just keep up with the fact that we take the first derivative and then say, okay, now we have a product, so we have to apply the product rule. So again, it's all a matter of what? Patterns. Product rule. And so when we apply the product rule, we see that our second derivative is now what? This function. Now, the secant function is even, f prime is odd. F prime is odd, therefore the second derivative is even. Okay, so we can do that cascading bit because we know those results about even and odd functions when we are concerned with differentiation. So we see that. So this was not taxing, but it's very important. That is, when you want to do a higher order derivative, you take the derivative of the derivative and you just move up in order. So first order, second order, third, etc. Okay, so derivatives, higher order derivatives are natural. That is, you just replace f for the second derivative with f prime. And then, of course, the third derivative would be replacing f prime with f double prime, and we just iterate. So there's nothing new to do, except we do see that the second derivative has a shape operation type formulation that's going to be very useful to us. We're going to call that concavity. Okay. Now, there is one thing that I want to say. There are some problems where you're asked to look for patterns when you keep differentiating, okay? And I want to show you one that comes up quite a bit. And this function is just 1 over x, and we want to look for a standard formula. So when we talk about power series in calculus 2 and Taylor's theorem, we're often find it useful if there is a formula for an nth order derivative that we can use it and simplify our calculations. So let's look at f of x and apply some real simple results. So when we look at f of x equal 1 over x, we're thinking, okay, well, that's a power function. So here's what we want to do. Find a general formula for, and now what we can do, ladies and gentlemen, we'll say, we don't want to put n tick marks. We'll just do n parentheses x, where n is a natural number. So we're thinking of, like maybe if we want to take a fourth derivative, is there a way to generate a formula for this? Because there's a pattern that develops. And in some, like I say, when you're differentiating sine and cosine, you get patterns because of the toggle between the two. Again, this isn't a feature that we will find with all problems, with all functions, but this is certainly a good example of using pattern recognition. So what we want to do is make this efficient. So what we want to think of 1 over x is just a power function like that. And we know that the power rule is good for all rational powers. And so we will make good use of this. So let's just start looking for a pattern. So we'll do f prime of x. So the rule is that we remove the power to a coefficient and then subtract 1. So this will give us -1, and then we'll have x to the -2. All right, so let's just keep going and see what we generate. F double prime, let's just keep going. This will be -1 times the -2. I mean, this is straightforward, but it's new. And then subtract 1. So now we just want to kind of see what's going on between the order of the derivative of these numbers here. Let's keep going. We'll do a three ticks for this. And then, of course, after that, we'll just start putting in the number. So now we have -1, -2, -3, x to the -4. So this, again, power rule. We talked about this last, and I actually proved this rule for a particular function, x to the 1/3, and that was interesting. And the nice thing about that is we don't have to do that every time. The abstraction gives us this very useful rule. Now let's do the fourth. Now what you're going to notice here is we're developing a factorial here. So we have -1, -2, -3, -4, x to the -5. And this just keeps going. So now what we can do, and we want to make a comment here, we see we have the 4, and we also have the 4 factorial there. So this gives us a 4 factorial, and it also gives us 4 negatives. So we have -1 to the 4th. So that's kind of interesting. If we look up here, we have the same thing. We have the 3 here. This gives us, in this case, n copies of -1 and a 3 factorial. Now, the other thing is this. This is just if we want the equals the negative of what? N plus 1. This is one more than the order. So up here, this gives us the negative of n plus 1. So this is an inductive procedure, but if we did another one, we get the same thing. So this is not something that occurs with every function. There has to be some type of pattern that generates, and because we've got a -1, we have a very simple deal going on. We find this to be the case with the binomial theorem that you will study in Calculus 2, a very beautiful result that has some really great arithmetic with the binomial coefficients. So now we can now, for instance, what's the word? Project a formula. And in this case, we can say, using these two as our models, we'll say the nth derivative evaluated at x will now be -1 to the nth power, n factorial, and then we have x to the negative n plus 1. So when you think about this, and what I've written here in my notes is that don't worry about negative powers or whatever. If you want to write that in the denominator, you can. When you're asked to actually create a formula, there may be some formatting issues or whatever, but now you can just see that if we wanted to use this formula for 3, we put in -1 to the third, 3 factorial, and then we've got a -4 here. So this clearly is, again, an inductive property that you could actually prove rigorously by induction. But I think we're at least fairly assured that if we continue with this, that this would be the result. And so this would be a way to generate nth derivatives of a function of this nature that has some kind of pattern. Now, of course, we look at tangent, that's a nightmare. I mean, tangent, we get secant squared, then of course we saw with this problem that we just did, if we start with secant squared, we get a bunch of secants and tangents just after a second order derivative, and then we do again, we're thinking, wow, this worked out. But when we look at something like that, we're thinking, okay, how do we do that? We don't, if I wanted you to take a second derivative or a derivative of this, a third derivative, then you could say, all right, well, that's secant times secant times secant, and use the product rule inductively. But you're not going to have to do that. That's going to be taken over by the next result, which will be a derivative of a composition. So we're not going to have to sweat these powers. I mean, you're thinking, what about power rules? What if you have a function other than x raised to a power? How are we going to negotiate that? We need a formula or a theorem that addresses the derivative of a composition of differentiable functions. And so you're thinking, boy, at this point, we really need it if we need to move on. But you can see here that the secant doesn't have the beautiful patterns that arise, or it doesn't appear that we're going to have something like that. But you'll find that there are cases when you do get something like this. And of course, once you figure this out, it makes the use of Taylor's theorem and the remainder for estimations much more easy. But whatever the problem requires, we just work with it. That's how we do in the calculus. Now, there was one thing that I wanted to address in a proof that I did in a previous lecture. And the essence of what I did, I think, was good, but I would like to offer an alternative that doesn't rely on a premise that I made that really did not focus on the appropriate arithmetic. Because as I went back and I looked at it, I said, well, that's a different way of looking at the opportunities that we have in the calculus. But by making a replacement, as I said, replace x with its additive inverse, the limiting process varies that way. There's something that you have to actually do when you make that change with the limit. And I did not make that change, but the way I finished the proof, I got the desired result. But again, that does not apply the arithmetic in the best way. So there's another proof in your notes, starting with sine and showing that the derivative is actually, starting with an odd function and showing that the derivative is even. And let me mention that to you, because I was making a comparison with this. So this particular proof, the one I did was even to odd. This is odd to even. And the way that you actually can move the proof forward is using identities and not necessarily doing a replacement until you just set a different variable. And that really is the best way to go, because when I was looking at my older proof here, I said, oh, this is really nice. And so when I compared it to what I was doing before, I'm thinking this is the best approach because it preserves the arithmetic. So let me go back to that theorem to say that suppose, so this will be an alternative approach that is correct. So suppose f is even, and we'll just say with domain odd. Again, that doesn't necessarily have to be stated, but we know that's symmetric by definition of even function. And then the result is, for instance, take take C element of I. So, and then I'll just say this, I'll just write this, then F prime is odd. So we're just doing kind of shorthand notation. So take C and I and consider, as we did before, the derivative of F at the additive inverse of C, because if indeed this is an odd function, then the negative will factor as we did in the previous exercise. But I want to show you a method that preserves the arithmetic. So now by definition, we have the limit as x approaches negative C of f of x minus f of the additive inverse of C divided by x minus the additive inverse of C. Okay, so that everything is the same, except we're going to let the use of identities drive the arithmetic so that we can preserve the limiting process, and then we can write in an equivalent limiting process that gives us the right variables that we need. That's the key. So we need to let the algebra move forward in a way that we preserve the arithmetic. So now first you can say, well, F is even, so the C here will absorb. So I'll just say F is even. So we have the limit as x approaches the additive inverse of C of f of x minus f of C. And then of course, minus the negative is x plus C. Now this is where we want to use a better choice of arithmetic. And it doesn't require any replacement, even though replacement is fine as long as you preserve the limit. But when you don't have a limit and you do a replacement, that's great. When you're doing transformations, that works beautifully. But here we still have this limit, which we can't ignore. So now we're going to use some identities. So we're going to say, well, we can replace x with its negative here. And that simply equals this because f is even. That's all I'm using there. So f is even, right? So again, here I'm using the hypothesis that f is even because f of the additive inverse of x is f of x. And now, of course, I can replace x. I'm doing a replacement, but I'm doing it relative to identities. So this will be the negative of negative x plus a c. Okay, now we're gonna think about what that means. Here's what's very important here. If x is approaching negative c, then equivalently, the additive inverse of x approaches c. And if we're going to make a substitution there, it has to be this. We can't make the replacement and ignore the limiting process. So that's what's important here. And so now we're like, okay, that's where we can factor. So we have the limit as x approaches negative c of f of negative x minus f of c. And now, of course, we'll factor one of the negatives. So we have the negative of negative x minus c. Of course, the negative preserving the positive here and the negative preserving the negative there. And at this point, we can now toggle. So now if x is approaching negative c, negative x is approaching c. So we have the limit as, and of course, with the chain rule, this is easy, but we don't have this yet. So we do this more elegant theorem using this approach that preserves arithmetic. And then, of course, the negative here we factor. And now this is actually the result that we need, but it's a little bit disguised. So you can just set beta equal to the additive inverse of x to make it more user-friendly looking. But that's exactly what we need, but it may be hard to see. So we have the negative limit as beta approaches c. So we're just making it look nice. So we have f of beta, doesn't really matter what we call it, f of c minus beta minus c, which is exactly the negative of f prime of c, which is what we wanted to show. So when you do it this way, the arithmetic of the limit is preserved. And this mimics what I did when I started with the odd function to get the even function. And of course, I think I was trying to be creative, and fine creativity is good, but it must preserve the arithmetic. So think of the using the definition of derivative and the even to the odd and the odd to the even using this kind of construction, and then you get a fluid proof that preserves the arithmetic. So again, I wanted to add that so you could add that to your arsenal of strategies, and plus take plenty of time to practice the quotient rule and the product rule. Of course, if you can master the quotient rule, the product rule is a walk in the park. I mean, it's simple, but you want to be able to use the building blocks of the simpler derivatives as you apply the quotient rule and the product rule, remembering the derivatives of the 6 trig functions, remembering the power rule, remembering the derivative of a constant is 0, and the derivative of just the variable x or z or whatever is just 1. Those are very special cases and very simple principles. And what's another principle we used a lot? The derivative of the sum is the sum of derivatives. And so all of these are very, very straightforward results, but they become more complicated as you have to put everything together. And then you want to break down your work systematically so that you can now solve problems with organization. So even though there are lots of examples to work, you're going to find that you're applying the same techniques over and over. And like I said before, be sure to break down your work into pieces where you get large fractions and things, break them down so that you can keep control over the arithmetic and keep the work less cluttered. I think you will find that to be very useful. Well, that's all I have to say for today. Like I said, the next result will be a huge plus to your computational ability. It will be the chain rule. And it is really one of the most important results that we will study in the course. I'll say that many times, and then you're thinking, how are we going to ever decide? But this is en route to the fundamental theorem of calculus. And then, of course, once we have that, we're going to look for other methods to integrate, which we'll find at the end of the course when we study your friends from college algebra and pre-cal, the logarithmic and exponential functions. So we'll see you soon. Take care.